My group developed a system that can heal wounds without scar.
Did you just say it heals without scars?
Yeah, it healed without scab or scar formation.
How could you say that just so casually? You should be jumping. Guess what my group found?
Wow.
This is StarTalk, Special Edition. Neil deGrasse Tyson, you're a personal astrophysicist, and since it's Special Edition, you know who else is my co-host. Chuck Nice. Chuck, baby.
Hey, what's happening, Neil?
All right, professional comedian and actor, of course, Gary O'Reilly. Gary, dude.
Hey, Neil.
Former soccer pro and soccer announcer.
Yes.
Your community of soccer players shares you with us, and I want to thank them for it.
I'm sure they won't care. Happy to get rid of me.
So, in Special Edition, as you know, we discuss things that affect the human mind, human physiology, just what it is to be human in this world, biochemically and physically. And this particular episode, the topic is, I love this topic. Let me get the human body in deep space.
Ooh.
Oh,
Yeah,
that's the best.
that is.
That's a good subject. Gary, how'd you and your producers come up with that one?
Well, we thought it was about time we sort of delved into some biomedical engineering, followed it with some regenerative medicine, and then decided, you know what, let's point it out into space and ask it to find ways to help the human body adapt to long-term space travel. If you remember, about 14 years ago or so, the 100-Year Starship Project from 2011, well, our guest was an integral part of that endeavor. So that's where we'll begin. We'll then hand over the floor to our Patreon listeners to answer their questions. So, Neil, if you would introduce our guest, and you'll find out where the human body and space will meet.
So yes, our guest today, it's not her first time. Oh yeah. We have Professor Ronke Olabisi right here in the StarTalk house. Professor, welcome back to StarTalk.
Thank you. Thank you for having me.
Yeah, so your background here, oh my gosh. If I did not do astrophysics, this is what I'd want to do. Your PhD is in
cool.
biomechanical engineering. Ooh.
Wow.
So you're the ones who invented like the Terminator, okay? Just let's be clear about that.
Yeah, that would be us.
living tissue over endoskeleton.
Let me hear you say, no, we would never do that. Let me hear you say that.
I mean, I would never do that, but I am sure that somebody would be like, that's cool.
Okay.
And if they could, would. But we're so far away from that right now.
And you also have a degree in aeronautical engineering. And so that would help get the space dimension of this biomechanical engineering off the ground. And like I said, you're a previous guest on StarTalk. So just welcome back.
Thank you.
And so, Gary, why don't you launch this rocket here? What do you have in mind?
Okay, Ronke, if I can call you that, or if you prefer Professor, remind us, if you would, about the 100-Year Starship Project and your area of involvement in what was the overall outcome.
Well, so it's not done because it's not 100 years yet, right? So
Point.
It's the Defense Advanced Research Project Agency, and it was initiated by DARPA in order to kind of inject an enthusiasm for space travel and spaceflight. If you look back at what the Apollo missions did for not just the economy, but for technology that we're still using today, it really transformed our world to the point that we're living in the space age. So like we have cell phones because they needed to communicate with the astronauts, things like that. And so the idea is we decided in 1961 to go to the moon and landed there in 1969. What if we had decided that in 1869? What would our technology and world look like today? And so that was the goal, to initiate, like, let's stop saying it's impossible, because in 1869, they thought it was impossible too. Let's just say, okay, if we can do it, what do we need? Well, we need, to go fast.
Wait, just to be clear, you're talking about traveling to the stars.
To another star. Yes,
star.
interstellar.
right now we're jet setting around the solar system. That's like nothing. That's,
Yes.
a few years here and there. So Starship was not just a poetic name, it's a destination.
It's a destination, but it's also a think project. So it doesn't matter if we don't get there, if we can get all the things that we need to do so. So in the same way that even if we didn't land on the moon, all of the technology that was built around trying to make that happen really transformed our world. And so if we decide that we need suspended animation, right? How is that going to help on Earth? Well, maybe you can get somebody, there's some fields where there's only 5 people in the world who can perform that surgery. And if their backlog is 100 patients wide, put them in suspended animation. Or maybe you're in a battlefield. Can you put them in suspended animation so that they don't bleed out, so that they don't die right there?
Or maybe you just really need a good nap.
Yeah, suspended animation.
So what you've done is ask yourself, what are the questions that we haven't yet thought to ask?
Yes. And so, like, better power, right? Because you would need a lot of power. And it would need to be sustainable because you can't take anything with you, right? So, I mean, you can't take the Earth with you, but you can't come back to resupply.
By the way, there's a movie called Wandering Earth where they do just that. They take Earth with them to visit the other stars.
I saw a Chinese language movie where
That's it.
That's it? Okay. Yeah, that was awesome. I loved that movie.
Wandering Earth, the sequel, is the one where they actually turn on the rockets and move Earth out of its orbit to the next star system, because the sun was misbehaving, and they said, and I just thought, they can't just fix, if you have enough power to move Earth, surely you can just go in and fix the sun.
Yeah, well,
yes, you
right?
have to suspend your disbelief for that. First, they stopped the rotation of the Earth. Then they put the rockets. And so all of the weather things that would have happened, it bothered me, but then you have to suspend your disbelief.
Yeah, that's why it's called science fiction. Yes. Okay.
Right,
Yes.
yeah. What bothers me is that we're taking everyone. That's the real problem.
Very nice way to see that, Chuck.
Yeah.
So Project Starship is not just biomechanical or biological, it's also the physics of space-time and how you're going to, and of aerospace engineering.
It's even textiles and clothing, right? So in the space station, I think it's like 900 pounds a year of laundry that they incinerate because they don't have laundry machines up there. So if you have to consider that, could you grow your own clothes and then just, instead of washing them, have them, I don't know, degrade and then grow some more? Or grow the materials to weave your own clothes?
All right, wait, Chuck, how long have you been wearing your drawers?
Right? Yeah. Exactly.
Now, I have an unfurnished basement. I'm sorry.
So it's things that we don't think about, but that would help on Earth too, because there's tons of clothing that doesn't get recycled, that just gets thrown away, and that's sitting in landfills. So
yeah, it's a huge problem.
Yeah.
Fast fashion. It's actually a very environmentally deleterious practice.
Even the production of certain cottons is toxic. But let's flick it back into your research, Professor. Healing wounds, building bone, growing organs.
Yes, tissue engineering.
Thank you. What a great
Love
term.
it.
Tissue engineering. How pivotal, how vital will that be if we are to be literally starships in the future?
If we're somewhere else and you suddenly find yourself needing a heart transplant, if I can grow you one, that's very important.
Yeah.
If you burn yourself and you need skin grafting,
skin.
and I can grow you skin, and particularly in microgravity, your wound healing is delayed and it doesn't heal in the same way it does on Earth. And there are a lot of different theories about that. Some of them are that we evolved in a gravity field and that the repair mechanisms require gravity to operate properly. But your immune system is affected, your microbiome is affected, pathogens become more virulent, and at the same time, your immune system is like, not today.
This is all because we did not evolve in space.
Yes.
Yeah. Kind of sounds to me like your real argument is we should stay home.
That's the final report to DARPA. 100-year spaceship, Starship, stay home. Yeah.
Neil, if you get ahead of a story before you get out into somewhere nowhere and go, oh, what do we do now? But if you think, okay, well, one immediate thing is the pharmaceutical. If you're a group of people on a spaceship traveling to another star, you don't just pop it to CVS, do you? There's not one on the way.
Right.
You can't get it delivered. You've got to take it with it. Could you grow it? Can it be developed? As the professor was saying, that the delivery systems and mechanisms to get wounds to heal quicker because you're in a microgravity. If you're ahead of all of those issues, then, you've got the walking, talking real Dr. McCoy. You've got bones on board.
Yeah.
So when you talk about that, are you using cells? Like we saw this during the pandemic, we used, it's why it's called messenger RNA.
Mm-hmm.
Are you using cells as delivery systems for healing? And, you take the cell itself and make it kind of part of the process of the healing? Or you put medicine inside of a cell?
Wait,
and
Chuck,
then
I have a
send
better
it?
question. So, Ronke, how do you do it?
Okay.
I know, I'm trying to figure it out. Hey, how do you do that?
So the paradigm of tissue engineering is you were getting there. It's cells, it's some kind of a scaffold, and it's biofactors. And so if you think about a building, when you're building a building, you put scaffolding down, and then the construction workers, they lay down the building, and then eventually they remove that scaffolding, right? And
Right.
they have these plans. And so in the same way, we try to tell the body, we want you to grow this. This is one way to do it. Other ways to do it are in a bioreactor, in an incubator. But one of the easier ways to do it is to convince your body to do it. And so I think maybe in the late turn of the century, you might have seen a rat with an ear on its back.
Yes, I saw
Yeah.
that.
And so it's easier to have the body do it if you give it the right instructions.
Wait, just to be clear, for those who did not see that picture, it was the cartilage of a human ear on the back of a rat.
It was grown on the back of a lab rat.
Right, not
Yes.
a rat's ear on its back. It was a
No. It was a human
on
ear.
its back.
Human ear.
And the rat didn't look too happy about that. I just thought I'd tell you.
He dug in his ear a couple of times, I think. But like every time I saw that, I just wanted to say, what? So what we do is with that scaffolding, we try to put these different biofactors that say, build skin or build cartilage or build muscle. And those are the instructions that are like the plans that you would give the construction worker. And then what you want is you want the body to then degrade that scaffolding. And the scaffolding can be lots of different kinds of things. But degrade that scaffolding, and then you're left with just the tissue. So it's no longer artificial. It is that fully formed tissue.
It's like the stitches that dissolve in your body.
Exactly.
All right, but what you're telling me is you're taking a path that's not the one we had all imagined from decades ago. From decades ago, we imagined, oh, if you need a new heart, I have this mechanical heart I'll now put inside you. I have a mechanical organ. Everything would come from the engineering side of this rather than from the biology side. So what is better about a bio organ if I can make a really good mechanical organ?
We've learned so much about biomaterials, and when you have these mechanical organs, you have to be on blood thinners for the rest of your life because they just like to form clots. They're also sites of bacterial infestation. You're constantly fighting all of these other things that are going on because your body is trying to get it out. And it's this foreign thing, it's get out. One of the hugest complications in orthopedic implants is if you get a bacteria, they'll form this biofilm, and the biofilm protects them from antibiotics. And so then they have to take out the implant because it's going to eventually kill you. If instead I could scrape some cells from the inside of your cheek and then grow you a new heart, and then your body doesn't reject it. Your body doesn't see anything wrong with it. It's not a site of infection.
Welcome home, heart.
Yes, and we don't need donors anymore.
Ronke, I'm very disappointed because this means you can't rebuild me better. All you can do is rebuild me the same way I was.
The goal with genetic and gene therapy is to maybe, if you have defective genes, we can replace those. And so gene therapy, some tissue engineering uses gene therapy in that it can tell the cells what to do by, genetically modifying cells that would normally do something else. You tell them, I want you to do this instead. Or you can do gene therapy to try to eliminate a deadly disease in people.
So why don't we do that to anybody and everybody that gets on Starship and give them this genetic upgrade? Guessing as much as we can what they're likely to come across from here to there. And as Neil said, build them better. Is that viable?
We're not there yet. It's not perfect. Gene therapy has had tragedies along the way, and so you want to be.
Wait a minute. You're burying the lead. Let's get to some of these tragedies. What are you talking about here, Ronke?
Chuck, just a drama junkie.
I need to know what these tragedies are. I have not heard about the tragedies of gene therapy. It's always heralded.
Bring it on, Ronke.
So I can't remember the disease that he had, but it was this young 18-year-old, and he had this disease. It was non-fatal, but it caused problems in his life. And the goal of it was to change this defective gene. And when they injected, I believe what happened was there was no response. And then they went over what the protocol said for the injection of the virus. And so he had a massive immune response because you have an immune response to virus particles. And so even if the virus itself it's non-replicating and it can't kill you, if you give a high enough dose, it's kind of like having an extreme allergic reaction. Your body goes berserk trying to attack those things.
Is that the cytokine? Is that the what?
Yeah, like it's a cascade. It's an immune.
Yeah. Most symptoms that we experience is the body's response to the pathogen.
Yes.
Okay.
And when you give that much, and they went off, and I think they found that one of the trainees, the postdoc, was fabricating data. Like it was this big scandal in the world of gene therapy, and people remember and don't want a repeat of that in everything that they do. So people want to be certain before they do anything that the same thing can't happen again.
Wow.
So regrowing organs is clearly an important ability to have on a generational starship. No doubt about it. But how about the ordinary everyday injury that people might suffer? A scraped knee, you cut the tomato too quickly, and you cut yourself. Have you been able to influence the rate at which someone heals relative to what biology would do all by itself?
My group developed a system that can heal wounds like 3 times faster, and it healed without scar. And so we want to move that forward because...
Did you just say it heals without scars?
Yeah, it healed without scab or scar formation. And so we want to move that forward and examine that and see if that works like in people in the same way.
How could you say that just so casually?
Because...
You should be jumping. Guess what my group found?
Because nobody believes it until you do it in a person. But you can't do it in a person until you establish it in smaller animal models, unfortunately.
So, Professor, are you talking about superficial scarring on the surface, or the internal scar tissue? There was no scar tissue internally?
There was no scar tissue in the entire dermis of the skin.
Wow.
And so we were like, this could transform plastic surgery. You wouldn't have to hide your scars up in your hairline. The hairline.
Exactly.
But not just like for people who want to look better, for people who have been terribly burned, for people who have been disfigured in car accidents, for people who have any kind of scar that they are self-conscious about. If we could like excise it and then put this on it and it would work, That's what we're trying to do. So we're using tissue engineering approaches to wound healing.
So it's not just a cosmetic side of it. I've had spinal surgery. I've had 3 spinal surgeries, and I have a foot-long scar. It's great. You've got miles and miles of scar tissue.
You know, Gary, I always knew you were spineless at some level there.
Neil, shut up.
Stop.
So, unless you work really, really hard to kind of break it up, just stops the mobility. And people have had orthopedic surgeries and are not able to do anything about it, are going to be rigid, and their mobility is really going to be compromised. So when you said no scar tissue, my eyes light up. That would be amazing.
Yeah, there's terrible contractures that particularly burn patients get, and it's life-changing, where some can't lift their heads, some can't move their arms anymore. It depends on the burn. One of the things that inspired me was just a devastating picture of a mother and daughter who had been burned. And I want to help those people.
Oh, that's amazing.
Gary, 50 to 70% of spine fusions fail.
I was lucky. I never got a fusion. I just had the disectomies and fractured facet joints.
Let me add one more question before we go to our Q&A, because Gary and Chuck have assembled questions from our Patreon fan base, and we value them highly. But I just want to give a little pop culture reference here. We've seen in the Marvel universe that Wolverine, and more recently he's done a film with Deadpool, I think they both have some uncommon ability to regenerate from injury.
So, but it's different. So, there's regeneration and there's healing. Wolverine heals. Deadpool regenerates. Because like when you watch it, it grows like it's a baby leg first.
Yeah.
As Wolverine is. So it's kind of cool.
Oh, so that's a difference I had not appreciated. So because we've seen Wolverine get shot, and then the bullet just sort of comes out of him, heals over, and there's no scar at all. So that's just healing on some superhero level. And Deadpool, you're saying, is like what a newt would do.
Yes.
The tail comes off, he just grows another tail.
Yeah. And he grows it in the same way that development, so embryonic development, that kind of thing. He grows it from baby sized leg to adult male. Whereas Wolverine, whatever was there before, just
comes back.
Yeah, exactly the way it was.
Right. Okay. And so how does that differ from what you do?
Mine in particular, I'm trying to do healing. And so regeneration is something that others in the field are trying to do. But I'm also trying to do de novo stuff. And so I can grow bone in patterns.
Did you just say grow a bone in a pattern?
Oh, wow. Yeah, we did that. It was very cool. We used seashells.
Now, exactly how close to Thanos are you is what I want to know.
Well, I mean, that bugged me. I was like, just make more food.
Yeah. Right. Just if you have that much power, just feed people, dude.
Yeah, the answers are out there.
It seems to me newts already regrow legs and tails in nature. Nature has already figured out how to do that. So how hard could that be to emulate that in human physiology?
So people are trying. People are trying to understand what's happening there. The thing about newts, I believe they don't achieve an adult form as well. And so it's like they're constantly doing embryogenesis type thing.
Oh, embryogenesis, that's what it's called. Okay.
I'm not an expert in this, so I can't really speak to but I do remember reading a paper where they detected electrical activity in the growing bud. And it's just really cool stuff that we don't do. I think they tried to replicate it in a lizard that didn't have the regeneration abilities, and they tried to replicate using electrical stimulation, and I think they got more than they did. And when you do electrically stimulate certain parts of the body, you get better healing, like bone. Bone is piezoelectric, which is kind of cool.
So before we get to Q&A, just, Ronke, tell us right now, I want you to commit, between Deadpool and Wolverine, which of them has more biomechanical authenticity?
I mean, neither.
Neither.
Those are not good choices. The way humans heal, Wolverine is more like a rapidly healing person, whereas Deadpool is more, his physiology is like more like a newt, but Wolverine would have scars. So the lack of scars is not authentic, and the growing new buds of embryonic like limbs is also not. No, both are no. Both are a big no, but they're fun.
Cop out. That's a total cop out. All right.
No, they're both no. I'm not choosing. I don't know.
I'm just saying, if he's embryonic, embryogenesis, if newts do it and Deadpool does it, it sounds like Deadpool is the natural winner here, except unless Wolverine got your no scarring formula from your lab. There it is.
Well, okay, it depends. If you're going to rate it, if we give it a rating scale, and so we give the scale on speed, the speed of healing, then Deadpool is more authentic. If you do it on the type of healing, then Wolverine would probably get like an 80% because it's more like the way humans heal, but it's without scar, so he doesn't get 100% of
He used your no scarring method.
Yes, exactly.
Yeah, but
he rated your lab.
it's too fast. It's too fast.
Okay, I got you.
It's too good.
Got you. Okay.
All right, Chuck, Gary, give me some questions from our people.
All right, let's start with David Klingbeil. Oh, by the way, these are all our Patreon listeners, and thank you for your curiosity, by the way. Dave's in Palmer Heights, Ohio. Could we, I'm guessing he doesn't include me, bioengineer people to function in both 1G and microgravity without harm from either environment, or do we not know enough about the effects of microgravity on the body to answer that question? Professor?
So the latter, we don't know enough. That one of the things that people are trying to figure out why it happens is something called SANS, which is spaceflight associated neuroocular syndrome.
SANS. Okay.
SANS. It affects the vision, and they're still debating on what causes that. And so astronauts are coming back nearsighted. When you look at the back of the eye, it's distended. There's different levels of impact on the back of the eye. Right now, it seems to affect men more than women, but there are not enough women to say for sure. So how do you treat something if you don't know what's causing it?
So I'm curious, because it can't be because they're in space necessarily. It has to be because they're in 0G, right?
Correct.
The air pressure around them is a little lower than typical, but if this was a symptom of air pressure, you'd find people living at high altitudes that have these same symptoms, but you don't. Is that correct?
Correct.
Okay.
And it used to be called something else, BIPS or something like that. They used to think that it was vision intraocular or intracranial pressure syndrome.
I just wouldn't think that my eyeballs would care which way the gravity vector goes, or if there's a gravity vector at all. Because my eyeballs work when I'm laying down, they work when I'm upside down, they work when I'm doing chin-ups.
But you're not upside down for months, right?
Oh, yeah.
And so one of the things that happens is you have this headward fluid shift. Like, think about the human as a giant balloon, right? So all of our blood vessels, they're kind of elastic, and the gravity is pulling down the blood towards your feet. When you go into space, it's not pulling down that blood, and you've got the muscles pumping everything up. And so in the same way, if I were to hold a balloon that was filled with water like this, it would be like a teardrop. But if I drop it in free fall and I watch it, the elastic will make it return to a round shape.
That's because all the water inside the balloon becomes weightless while it is falling.
Exactly.
And that weightlessness then changes the shape of the balloon.
The weightlessness allows the tension in the balloon
surface
to pull equally, and so then it becomes a sphere.
Right.
So in the same way, when we're standing on Earth, we've got more of our blood pulled at our feet, and then we go up into space, and then all of the elasticity of our vessels pushes that blood to a different space.
We should send only far-sighted astronauts into space.
Yeah.
Because there's a short-sightedness force operating on it, and they could come back with regular vision.
Oh, yeah.
It doesn't quite work like that.
Spaceflight isn't the LASIK surgery for far-sighted people. The most expensive LASIK surgery
That's
ever.
what that would be, for sure. Gary, what do you have?
All right, Vincent Zimmerman, who's from Pennsylvania, says hello, Neil, Chuck, and myself. My question is, could we bioengineer astronauts to be more resistant to radiation?
Oh.
From what I understand, radiation is a concern.
One.
Yeah. And so
the big one.
There you go. That's the nub of the question. And he says, loves the show.
So, okay. A lot of people are asking about bioengineering people. And that's really not, for the most part, what most researchers do. Now, that having been said, like what we're looking at is we're looking at bioengineering certain things to get you back to your normal state, not bioengineering you to give you superpowers. That having been said, right now, there is a bioengineered form of melanin on the ISS, and it can withstand certain kinds of radiation that regular melanin cannot. And if you don't remember what melanin is, it's what makes me brown. They believe that because there are so many different kinds of melanin, that maybe somewhere on Earth, this kind of melanin exists. I believe it has like a silica in it instead of what I don't remember, but it is a paper that I read, and they're looking at ways to use that. And the goal, I believe, was to use it as kind of a lotion. So the way we have sunscreen, this would be like cosmic radiation screen. But again, when you're talking about cosmic radiation, some of those particles, nothing stops.
Well, listen here, Tim Johnson. It's great to have you aboard the space program. Some good news and some maybe better news. The good news is you're accepted. The different news is you're going to have to be black. So we need you to put this cream on.
So it's also true, and I think we've known for a while, for example, when fighter pilots go into tight G turns and the blood leaves their head and goes into their legs, the question was, do we create some kind of medicine, a pill for them to take, where the brain retains its oxygen, even though blood is going down, retains what little oxygen it has, even though the blood is going to the foot. The solution to that was pressure pants.
Squeeze their legs.
You squeeze the leg. It was an engineering solution to the biophysiological problem. So for me, the damaging radiation question is easily solved by shields.
Make a radiation shield on the ship itself.
On the ship itself.
Right. So that way you don't have to.
It's a very good high energy absorber of energy. The water could have a skin that's filled with water, and you cycle water in and out of it. I mean, that could work too. I'm just saying.
Oh.
I mean, you would have to have, I think they calculate it as a foot to make sure you block everything.
A foot of water?
A foot of water around the ship, which is extremely expensive.
Maybe it's a jacket the ship puts on once it's already in space. You know, you kind of. It's like you get to a dock and you slip into your little spaceship jacket, and then you move.
I mean, it's
a proof jacket. All right.
It's funny. I talked to a fighter pilot, a captain, and he said women are G monsters, right? And he said all the women do better than the men at withstanding the high Gs because our blood vessels are smaller and more resistant, and so it takes more for the water. And in the same way, in many ways, women do better in space for multiple reasons like that. But you bring up that one of the things to reverse the headward fluid ships is a lower body negative pressure suit, where they essentially try to suck your lower half of your body to keep the blood from going up into your brain and causing all kinds of problems.
Okay.
Yeah.
Like a compression suit or part of a suit.
But the reverse.
Yeah.
It sucks. It's just a vacuum.
All right, keep the questions coming. What do you have, Chuck?
This is Zach Kellogg. Greetings, Dr. Tyson, Ronke, Chuck, Gary. Zach here from Springfield, Missouri. My question is regarding the cell therapy at the Olabisi lab. Is it a plan to use cell therapy to assist in sustaining and building bone density that astronauts lose in space travel, especially in the future extended space travel? Thank you for all that you do. So when they get back and they're all atrophied, would you be able to use cell therapy to help them along the way and when they return? Or is there preventative things that you can do? Well, exactly. I mean, that's a real problem. What he talks about is bone density for a long time in space.
It's a really interesting question. It's what happens, and this is why it's so hard to study. So what happens, you've got these bone building cells called osteoblasts, and you can remember osteo is bone, blast is build. And you've got these bone cleaving cells called osteoclasts, and they eat away your bone. Now imagine, and this is really, I think it's Llewellyn Starks is a perfect example of this. He was a high jumper and he just broke his leg right in the middle of long jump. And if you think about how, I think everybody here has taken a soda can and bent the tab back and forth until it broke, right?
Absolutely.
So you are fatiguing that metal. And once that metal is fatigued, it just breaks.
Yes.
No matter how old you are, your skeleton is at most 10 years old, because otherwise, just daily living, you would be fatiguing your skeleton. And so those osteoclasts go in and they cleave out those tiny microfractures, and the osteoblasts come in and they put new bone in. And so there's slow turnover, but over time, everything is replaced. Now, when you go into space, what happens is that the osteoclasts are still like, yeah, I'm doing my job, but the osteoblasts are like, not here, we're not needed. And so this is part of the reason that, astronauts are susceptible to kidney stones. Everything in your body relies on calcium. Your muscles cannot function, including your heart, without calcium, right? And so calcium is stored in your bones. And when you degrade your bones, you're dumping a lot of calcium into your bloodstream. And then you get things like kidney stones and, all kinds of problems. But one of the things that they can't figure out, because if we put these bone cells in a petri dish, they don't act the same way as they do in the body. So we can't study it that way. We can only study living beings. And when you try to stop this process, you can't encourage the osteoblasts to continue doing their job. What you can do is you can stop the osteoclasts from cleaving the bone. Right. Wow. And so you're stopping them from cleaving the bone, and you get it does work. And these bisphosphonates, they've tried in women who are getting osteoporosis, and it works great. But in 5% of them, what happens is that same thing that happens to the soda can. Without that turnover, they'll be walking and they'll be like, my leg is a little sore, and then snap.
Snap.
Yeah.
Wow.
And there's these terrible breaks. And then you have to stop.
Is there a way to stimulate the osteoblasts while they're in space? So not chemically or even,
exercise.
Just like some kind of pounding or stimulation that you could. Because one of the things that they tell you to do, like if you want to create bone density here on Earth, like jump rope or, do something that gives some slight stress to the bone itself.
Yeah. And so that's why they exercise like 2 to 4 hours a day on those treadmills with the bungee cords.
Yeah, of course, all this is moot if we rotated the space station. Then you have this ring of 1G, and then it's no longer a variable.
You don't care, because now you're on Earth the whole time that you're traveling.
Yeah.
There was supposed to be a module where they tested that, and I think the module got scrapped because they couldn't figure out. It wasn't intended for the whole space station to rotate. It was intended for just a module to rotate, and people could go in it. And I think it's on display in Japan because it got partially built, but they couldn't figure out how to keep it from vibrating the rest of the station, and were worried that it could be catastrophic. So to go back to his question, one of the things that they do is they kill the osteoclasts. One of the things that I'm trying to do is I'm trying to encourage the osteoblast by using the seashell stuff where we did it in patterns, and we can use antibodies to go to the sites where the osteoclasts are killing everything and attract the osteoblast to go back to those sites. So that's just what we're trying to do.
Bone wars. Yeah.
Professor, you just said seashells. Is that in some of your work you use mother of pearl?
Yeah.
Explain that a bit more, because seashells is just you brushing over the surface there, I'm sure.
So it's really, really, really cool. And it goes back to like 7th century BC with the Maya. I'm sure you've heard about like tooth implants and how people are getting tooth implants. And maybe you know somebody whose tooth implant failed. Well, they found this portion of a Maya skull where in the jaw, initially they thought that the 3 mother of pearl teeth that were there were put in for the funeral so that they, their corpse would look pretty. But then this dentist was like, can I x-ray that? Because he saw it in a museum. And they let him x-ray it. And it showed that it had been implanted during life and that it had stayed, that it had grown bone into the implants. And so that person had functional teeth that last longer than what we can do, because it's lasted like thousands of years after the person is only now a piece of a jaw, right? And so when this was discovered, it sparked a lot of interest and research into mother of pearl as a biomedical implant. And this one group, it was really cool. They took these osteoblasts, the bone cells, and they put them in a petri dish, and they took a chunk of bone on one side and a chunk of nacre on the other side. And the nacre side, little mineralization that looked like nacre started growing towards the bone. And on the bone side, little mineralization that looked like bone started growing towards the nacre, and they met in the middle.
And that's how you know it's an active biological process.
Yes.
And I think archaeologists discover this in bone remains. They know if the bone had healed from an earlier fracture.
Exactly.
Because cavemen were breaking their stuff all the time.
Yeah.
Mm-hmm.
Yeah.
And like a whole lot of research sparked out of this, and people identified that it was certain proteins within the seashell that were responsible. And so my group took those proteins and we put them in microscopic patterns to see if we could make osteoblasts do what we want. And we could. That was cool.
Oh my goodness. Is there anything you can't do?
I know, she's Frankenstein, right?
Oh my goodness.
The doctor.
Teleport. I want to teleport. I would go to space and hang out.
Right on.
Teleport. We'll get you some wormholes. I'll trade you a wormhole for your human making machine.
Deal.
Gary, we've got time for one last question.
All right, let's go to Greece. This time's in Athens. We're going to get a question from Elias Siametis. Hi, everyone. Let me see if you can pronounce that, Chuck. So I did it for Chuck. We can't go faster than light, and we can't hibernate. Hence, for extended space travel, we'll most likely live through it for some form of synthetic integration. While I find it to be a plausible scenario, how can we marry biology to synthetic materials in a way that our cells are either replaced completely by inorganic ones or revitalized in a way that they don't decay, which I kind of think borrows back into that last answer you were giving with mother of pearl. So please, Professor.
Because if you freeze a T-bone steak, after 3 years, it's really different from what you first put in the package. Like the proteins are degrading, it's dehydrating, there's things going on inside of it, even though it's in a deep frozen state. So if you can preserve a human body so that it can pop open and wake up at the end, what are you doing to it, if that's even possible at all?
So we can freeze cells fairly easily. I think the record for somebody defrosting an embryo is 20 years, and they became healthy babies.
Wow.
We use
with
something...
a job. Came out with a job. 20-year-old embryo came out with a job. Like,
Or do you went to college?
Oh,
But yeah, that's the dimethyl sulfoxide, DMSO we use. I think they use something different for embryos, but we use that because it kind of acts like an antifreeze, and then you freeze it slowly, and then you use liquid nitrogen to really, really minus 165 degrees Celsius, keep that cold. But in his question are several assumptions. So there are researchers who are working on warp drives, and they're getting successful and interesting results. There are people who are working on torpor, which is a kind of hibernation, and they're trying to make non-hibernating animals hibernate. And so, like, when we talk about suspended animation, we're really just using science fiction words for torpor and hibernation. But there are researchers who are trying to do that because the benefits to having somebody in surgery under torpor, then maybe you don't need to use a ECMO machine, which is a heart-lung bypass, which, affects people differently. Maybe you just put them in hibernation and then you can do the surgery and then you can wake them up, and you never needed to run their blood through an ECMO, stands for extracorporeal membrane oxygenation device. The things that we're trying to do, people are trying to create cells from just the raw chemicals, like living cells. And the reason is because they want to understand how life began. And so at that point, I don't know that people are trying to use those cells and replace body cells. What people are considering doing, and this is how we immortalize ourselves. So I actually have cells that are kind of like, more like Highlander than like Wolverine. And so like we use immortalized cells. And immortalized cells, you have things called telomeres, and the telomeres are kind of like a fuse on the cell, and it can replicate itself until that fuse runs out. And each replication, that fuse gets shorter, and that is the senescence of the cell. And people have linked the length of the telomeres to aging, and people who don't age as quickly seem to have longer telomeres in their cells.
There can be only one.
Exactly. It's not causal. And so we don't know the correlation. It's a correlation, but we don't know that it's causal, I should say. And when we use these cells that we're doing our experiments on, we don't want cells that are going to be no good after like 50 times that we replicate them. So we modify these cells so that they can replicate indefinitely. And this is called immortalized. So we use immortalized cells. So they won't die from replicating themselves. They won't achieve senescence, but we can kill them by like pouring bleach on them. That kills them very quickly.
Oh, man. If only you could have done that to Highlander.
You can kill a Highlander, but otherwise they're immortal.
Yeah, you got to cut their head off, though.
Yes.
A little bleach would have been a lot easier.
Well, bleach is decapitation for cells. It causes...
President Trump wanted you to put bleach in your body to get rid of the
There can be only one. That's what I'm saying.
It will kill your cells before it kills anything else.
Right? It's better to burn out than it is to fade away. Okay.
We've only just begun to plumb this topic. This is, and every next interview we have with you, Ronke, it makes me wonder. We want to meet your husband and like poke him, make sure he's real next time.
Yeah.
Okay.
Yeah. I want to see if he has those immortalized cells. That's what I'm looking for.
Ronke, thanks for doing yet another StarTalk with us.
Thanks for having me.
Yeah.
We're going to come back for more for sure. And just if anything, to find out what the latest is coming out of the lab. That's what we come up to the lab and see what's on the
horizon.
No. Come up to the lab and see what's on the slab.
Aha.
I see you shiver with anticipatory
quivers.
Okay. All right, Professor, we'll come and find you again.
Yes.
Okay.
Yeah. Thank you so much.
Gary, always good to have you. Chuck.
Thank you, Neil.
Always a pleasure.
Neil deGrasse Tyson here with another installment of StarTalk Special Edition. As always, keep looking up.